Great pleasure to welcome Yann LeCun, who will be our first invited speaker. So while Yann is setting up, I cannot resist to say a few words. Of course, Yann does not need any introduction. Everybody has heard about Yann, and it suffices to say that he is the head of AI research at Facebook at the moment. But I've known Yann since we were PhD students, and it's an incredible travel that he has made since then. Already in the 80s, he was passionate about neural networks, and this was the subject of his PhD thesis. And he's one of the inventors of an early version of the backpropagation algorithm with which you couldn't do anything with neural networks today. And Yann went on after that to do a postdoc with Jeff Hinton, which is, who everybody knows also in this field. And then went to work at AT&T Bell Laboratories with a great number of researchers that have now, founded research at NIPS to a large extent. And I just wanted to mention an anecdote before Yann puts up his slides. When we were at AT&T, once we were sweating on some projects, and somebody turns to Yann and says, and what if it doesn't work? What is plan B? And Yann says, there is no plan B. It will work. And so I think this is the story of, Yann's life. Yann does not have plan B. It has to work. And this is what has been, his success throughout the years, even when there were downturns in the neural network field. He never lost faith. He knew, he had to work, and in the end, it did work. Yann LeCun.
Well, thank you, Isabelle. I actually don't remember this episode, but it could very well have happened. It probably did. So this is my plan A for the next 10, 20 years or so. So I'm going to talk about predictive learning. This may not be perhaps a phrase that you have heard in the past, and really it's kind of a renaming of relatively old things. But before I talk about this, let me show you a picture. I see Terry here down there. He knows that picture. This is a picture of the participants of the first connectionist summer school that took place at Carnegie Mellon in July 1986, so a little over 30 years ago. And this was kind of the start of the neural net community, if you want. And it was co-organized by Jeff Hinton and Terry. And there's a lot of people in this picture that you may or may not recognize, and so I'm going to help you a bit. Jeff and Terry are down at the bottom, as well as Jay McClelland. I'm sort of hidden in the pack here, the top left. There is Michael Jordan, still a PhD student at the time. Rich Sutton, Andrew Bartow, not Rich Sutton. And a bunch of people that went on to do great things, some of them in machine learning, some of them outside machine learning. Okay, better microphone? Okay. All right, apparently that's a better microphone. Okay, so we all know about supervised learning, of course, right? You take a bunch of samples, you run them through the machine, and when the machine doesn't produce the answer you want, you adjust the parameters on it, the knobs, of which you may have hundreds of millions in modern systems. And if you do this enough times, the knobs eventually settle on a configuration that you hope will recognize all the things you've trained it on, but hopefully also will recognize the things it hasn't been trained on that are similar. And over the last several years, as you know, we've seen a kind of a change from traditional methods in pattern recognition and machine learning towards deep learning, where all the layers are trainable, and that has led to great success in image recognition using convolutional net that allow us to build hierarchical representations of the world. an interesting thing is that there's been an inflation of the number of layers in those networks in the last few years, that you have now practical networks that are used every day by companies like Facebook and Google, etc., Microsoft, that have maybe 100 layers. And that's the kind of inflation that I wasn't predicting back 20 years ago, certainly. So in particular, one thing that has become very popular in recent years is this idea of ResNet, which is a neural net that's essentially by default an identity function, and where the network part of it learns the kind of nonlinear part deviation from the identity function, and that allows us to train very, very deep network. This is an idea from Kai-Ming He, who came up with this when he was at Microsoft Research Asia, who is now at Facebook AI Research in Menlo Park. And what convolutional nets and deep learning have allowed us to do over the last decade or so is do things like drive robots around by kind of learning the traversability, applying convolutional net convolutionally on the image so that it can label every patch in the image and eventually drive a robot properly. We've used convolutional nets to do semantic segmentation. There's been a lot of progress over the last few years. This is a 5-year-old paper, but there's been a lot of progress over the last few years on doing this, and so much progress, in fact, that some systems that are for self-driving cars actually use the basic idea of semantic segmentation. So systems that are produced by companies like Mobileye or NVIDIA, etc., use convolutional nets to recognize obstacles and detect them, to locate them, to label the entire image as to whether it's traversable or not, to produce proposals for steering angle for the car. And there's been really impressive demonstrations, even deployed products that use those things. So a lot of impact. More recently, convnets have been used for things like not just recognizing objects, but also outlining their contour. Again, it's just supervised learning, a convolutional net, which is trained to produce a category as well as a mask for the object, and it produces object proposals. Some version of it that was produced at Facebook AI Research in Menlo Park was recently open source, so you can just download the code and kind of use it in your research. It's called Sharp Mask. There's 2 versions, Deep Mask and Sharp Mask. And the results of it are pretty astounding, at least for some computer vision researcher who would be transported from 5 years ago to today. Looking at results like this, I think would be surprising that it happened so fast. So those systems can identify cell phones, people, laptop, and outline them. Can pick out people who are behind chicken wire and fuzzy people in the background and tell that there's a frisbee, pick out broccolis in Chinese dish, and do amazing things like count sheep and tell one sheep from another. So those tasks are really complicated because there's nothing that looks like a sheep than another sheep that stands behind it. And so it's kind of amazing that this works so well. And it's pure supervised learning. But the problem with supervised learning is that you need human-supplied labels. You need 2 things for supervised learning to work. The first thing is you need people to basically label images or whatever it is you want to recognize. If you want to do language translation, you have to have parallel text and things of that type. And the other thing you need as well is you need those labels to be somewhat reliable. If they are categorical, that means the image has to be more or less unambiguous, and you don't want too much of an error rate in the labels, the provided labels. And that's a limitation because that means the amount of information that the machines can be trained on is relatively limited. It's limited by how much reliable data people can input in the system. So in my opinion, that's one major obstacle towards AI, and there are others. So let me speak to this. What are the obstacles to AI? What I'm interested in at Facebook and at NYU, and that's been kind of the project of my life, if you want, is to understand the principles behind intelligence, whether it's natural or not natural. And And of course, as an engineer, the best way to understand something is to build it. So kind of, building intelligent machines verify whether the hypotheses about the nature of intelligence are correct by building a machine that actually reproduces the functions of intelligence. And very early on, I thought that learning was an intrinsic part of intelligence. You don't really have any intelligent entity that that we know around, at least not generally intelligent entities that don't have the ability to learn. Okay, so what are the real obstacles to AI? If we think about the architecture of an AI system, we need machines to be able to understand how the world works. I'll come back to this at length. So understand the physical world, understand the digital world, of course, understand people. Understanding people is probably one of the hardest part there. They need to acquire some level of common sense. They need to, and to do so, they need to learn a very, very large amount of background knowledge, mostly through observation and actions. So babies, for example, in the first few hours, weeks, or months of life, learn a huge amount of knowledge, background knowledge about the world. We're not born with the idea that the world is three-dimensional. We're not born with the idea that there are objects in the world. We're not born with the idea that objects don't disappear spontaneously. We're not born with the idea either that an object that's not supported will fall. So a lot of those concepts we learn in the first 6 months of life. And some concepts like the idea that an object doesn't fall if, an object will fall if it's not supported, we actually learn between the age of 6 months and 8 months. That's relatively well measured. So those are really very basic things that we learn by observation, by experimentation. And it's a much, much larger amount of information than the kind of information that our machines are learning through supervised learning. So we need to perceive the world to be able to, we need machines to be able to perceive the world. We need them to be able to estimate the state of the world. We need them to be able to plan in such a way that the world will reach a satisfactory state to satisfy a goal. And so perception plus predictive models, which essentially are ways to predict where the world is going to go, plus memory, that's necessary for that, plus reasoning and planning, that's what makes an intelligent agent. Okay, so I mentioned the phrase common sense. What do I mean by common sense? What is common sense? It's a very old classic problem in AI that of the fact that machines don't have common sense. So even though they might have some knowledge on a very narrow area, as soon as you get out of this area, for things that we take for granted, their response is usually stupid. So for example, there is a very well-known set of sentences called Winograd schemas of the type, the trophy doesn't fit in the suitcase because it's too large, or the trophy doesn't fit in the suitcase because it's too small. So in the first case, the pronoun it refers to the trophy, and in the second case, the pronoun it refers to the suitcase. And to be able to lift this ambiguity, you have to kind of know how the world works, more or less. My colleague at NYU, Ernie Davis, actually has a list of a couple hundred of those sentences that people have collected over the years. There is an annual competition where computers sort of try to figure out what the pronoun refers to, and the best performing machines are below 65% correct. Humans are above 95. Similarly, if I say, Terry picked up his bag and left the room, there is a lot of information you can fill in. There is a lot of missing information in this sentence that has a few words, but there is a lot of information you can fill in by just knowing how the world works. You know that he has to stand up, extend his arm, grab his bag, closing his hand, most likely. He's probably going to walk. He's probably not going to fly or dematerialize like this gentleman here at the bottom, although he does have superpowers. And he's probably going to walk towards the door, open the door. He's not going to walk right through the wall. There is a lot of things like this that we can infer about the scenario of the sequence of events that have to occur because we know how the world works. And the knowledge of the world, the constraints of the world, allows us to fill in the blanks from this kind of short sentence of a few words. That's, I think, what a lot of people call common sense, the ability to fill in the blanks. So how do we get machines to learn this? So common sense, perhaps, is the ability to fill in the blanks. That means inferring the state of the world from partial information. So we don't have perfect information about the state of the world through our perception. whatever perception we have is very local in the world anyway. So inferring the state of the world from partial information seems like something that's very important if you want to have an impact on the world. Even if this impact is just moving an object or something like that. Common sense is inferring the future from the past and the present. It's also inferring past events from the present state, particularly useful if you are a policeman or a police inspector, right? You get to a scene and you have to figure out what happened. It means very basic things like filling in the visual field at the retinal blind spot. We have a blind spot. That's where at least all vertebrates have a blind spot. That's where our optical nerve punches through our retina. Invertebrates are better designed than we are. When they're not in the same local minimum of the fitness function of evolution. The wires come at the back of their retina. So we have this blind spot, and we're not conscious of it because the kind of low-level visual cortex in our brain kind of fills in the blank, if you want. We can do things like complete occluded images and sort of infer what's behind an object if we have some idea about what the general shape of the object is. Perhaps if you are on this side, you only see my right profile, but you can pretty much infer what my left profile looks like. Predicting the consequences of our actions, that's very important, of course, to be able to plan. Predicting a sequence of actions that will lead to a particular result is also, of course, very important. So really, filling in the blanks mean predicting any part of the past, present, or future percepts from whatever information we have available. That's what I call predictive learning. But in other terms, a lot of people would call this unsupervised learning. Now, unsupervised learning also means a lot of other things, and sometimes is taken as a very narrow meaning, and so that's why I prefer to use the word predictive learning. So it doesn't necessarily mean predictive in the future, but it means filling in the blanks. But really, it's unsupervised learning. So the necessity of unsupervised learning is follows from this argument that I've heard from Jeff Hinton since I've known him, which was in 1985, I believe. And it's related to the fact that the number of samples that are required to train a learning machine for any task depends on the amount of information that we ask it to predict. So if you train a neural net to do binary classification, you can't make the neural net very large unless you have tons of data, because the amount of information you ask it to predict is very weak. So for example, some of the first experiments that we did with convolutional nets on real images was for phase detection or pedestrian detection. And it didn't work that well. It worked fine, pretty much at the state of the art, but not spectacular, partly because the data sets were small, but also partly because the task is extremely weak and provides very little information about the world. If you do something else, if you train your convolutional net on ImageNet, which has 1,000 categories, and then you fine-tune it on a task of this type that's very weak in terms of label, it works much, much better. And it's because there is a lot of things about vision that are common to almost any task. And so if you train the system on a generic task in which you give it a lot of information to predict, you can then specialize it to any task you want. Again, it's called transfer learning. So here is Jeff Hinton's argument. And this is kind of a copy-paste from an answer to a question that Ask Me Anything on Reddit a couple of years ago, but he has been saying this since the late 70s, or at least the early 80s. The brain has about 10 to the 14 synapses, which means parameters if you want, and we only live for about 10 to the 9 seconds. So we have a lot more parameters than data. This motivates the idea that we must do a lot of unsupervised learning, since the perceptual input, including proprioception, is the only place we can get 10 to the 5 dimensions of constraints per second. So this stems from the idea that you need roughly as much data as you have training samples. He was thinking about input data, but really what it really means is how much data you ask the machine to predict. That's kind of how you train a machine. A very powerful machine, you have to ask it to predict a lot of things. Otherwise, it's going to be degenerate. So that led me to draw a slightly offensive slide, and I apologize in advance. And I've taken some heat for this, but I promise I'll make it up, okay? How much does a machine need to predict? So depending on the mode of training of that machine, it's going to get different amounts of information that it's going to be asked to predict. In pure reinforcement learning, by which I mean you train the machine to predict a value function as a function of an input and an action, for example. The only thing you ask the machine to predict is a value function. It's a scalar. Moreover, you only give it the scalar once in a while. But let's assume you give it at every time step or every trial. Okay, so there is no temporal dimension to this. The amount of information you give to the machine is extremely weak, extremely poor, and there's basically no way a large machine will learn anything useful unless you provide it with millions and millions and millions of examples. So in its purest form, in which you ask purely the machine to predict a scalar, and that's the only information you kind of provide it if you want, this type of pure reinforcement learning just can't go anywhere. Supervised learning provides a bit more information to the system because you provide a label which may contain a few hundred bits or something of that type, maybe 10,000 bits or so. But it's still very weak, and the amount of data you can train on is whatever has been labeled by people. So predictive learning is where the bulk of the information is, and you have to ask the machine to basically predict the world. And that way you can provide it with millions of bits per sample that it needs to predict and perhaps train very complex machine to learn complex dependencies about the world. So it led me to this kind of half-joke analogy of if the intelligence is a cake, the bulk of the cake, the genoise, if you want, is unsupervised learning, the icing on the cake is supervised learning, and the cherry on the cake is reinforcement learning. And I must admit this is slightly offensive to people who spend their days working on reinforcement learning, but I'll make it up, I promise. I'll make it up because there is a form of reinforcement learning that actually uses unsupervised learning as a kind of a submodule, if you want. So first of all, reinforcement learning is really important. You need to be able to kind of train a machine to maximize some value function or whatever by figuring out a sequence of actions. And in fact, we're working on this at Facebook AI Research. In fact, this is some work led by Yann, who is at Facebook AI Research in Menlo Park, of training a machine to play Doom, and he actually won the last competition, the so-called VisDoom competition. So this is using basically a convolutional net looking at a picture and being trained, with details that I won't go into, by reinforcement learning to win. So it works in this case because we have tons of examples. We can basically have the machine play millions and millions of games. We can simulate the game really quickly. Here is another example. This is work by Gabriel Sinev, Nicolas Zunier, and a few others at Facebook AI Research. And this is using reinforcement learning to train in the sort of battles in the StarCraft Brood War game. So this is the first version of StarCraft. And in fact, we just, it's invisible, but we just released a piece of code that interfaces StarCraft Brood War to Torch, which is the deep learning environment that we use at Facebook, and that allows you to kind of plug deep learning into StarCraft. And so those, this reinforcement learning, actually classical reinforcement learning doesn't quite work there, so Gabriel and Nicolas had to come up with slightly different techniques there to get this to work, but you can train those things to kind of figure out really what the best strategy to deal with an opponent. Okay, so here is a nice quote from, I don't know if Rich Sutton is in the room. I know he's in the city, but, oh, right here. Hey, Rich. Hey, this is copied from your paper about Dyna. So Rich had a paper about 25 years ago called Dyna, an integrated architecture for learning, planning, and reacting. And there's this little quote in this paper that I like very much. It says, the main idea of Dyna is the old common sense idea that planning is trying things in your head using an internal model of the world. And there's a bunch of references for people who, of course, formulated this idea, including himself 10 years before with Andy Bartow. This suggests the existence of a more primitive process for trying things not in your head, in the world, but through direct interactions with the world. Reinforcement learning is the name we use for this more primitive, direct kind of trying. And Dyna is the extension of reinforcement learning to include learned world model. I think this should be the philosophy of most work in reinforcement learning nowadays, because although what people now call model-free reinforcement learning has a very, very bad sample complexity, what we now call model-based reinforcement learning, which is really what Rich is proposing here, is considerably better because it takes advantage of unsupervised learning. So I'm going to go into this a little bit. But before that, I'm going to talk about classical control theory. So in classical control, optimal control, you want to control what control theory is called a plant. It's always called a plant, regardless of what it is. So you have a plant simulator. It's basically a model of the real system you want to control. You might have identified the parameters of this model by just observing the plant in various conditions. But now you have this plant simulator, and the advantage of the simulator is that it's differentiable. So you can plug a command at time t, run the simulator for one time step, and then you get the next time step, and then you can produce another command, run the simulator again, and this is like a recurrent neural net, except it's not a neural net, it's a hand-built model. And the way optimal control works, sort of classical methods for, say, computing the trajectories of rockets or something like this. This is the technique NASA used in the 60s to compute rocket trajectories, is that you figure out the sequence of commands that will minimize a particular objective function while perhaps taking the state of the plant at a particular state, at the end, or minimize the time it takes or the energy it takes to get there. You should sort of encode this in the objective function. Now, because all of this is differentiable, you can use gradient descent to do this planning. This is a very traditional classical technique in control theory, which, in my opinion, a lot of machine learning people have forgotten and should probably exploit a bit more. So having a differentiable model of the world brings you this ability to do planning through gradient descent. And that's a very, very powerful thing, because we know gradient descent is much more efficient than combinatorial search. Okay, so now I'm ready to talk about what I think should be the architecture of an intelligent system. And this is a diagram that you've probably seen in papers going back to the 80s, where an intelligent agent produces actions that have an effect on the world, and the world responds by producing percepts, which the agent uses to estimate the state of the world, essentially. Now, in classical reinforcement learning, or in a lot of classical settings for this kind of thing, the reinforcement comes from the world to the agent. In this thing here that I mentioned, the objective is a function of the state of the agent. Basically, the objective is some sort of immutable function, hardwired immutable function, if you want, that tells the agent whether it's happy or not. And we have that in our brains. There is, things at the bottom of the brain that basically tell you if you're happy or not, and you kind of try to keep that thing, in a particular state. So that's called intrinsic motivation in the context of reinforcement learning. And so it's a bit different from the sort of classical model where the reinforcement comes from the world. Okay, it's sort of intrinsically generated in this case. Okay, so what structure does the agent have to have if you want it to act intelligently? And basically, that's where this idea of a world simulator comes in. Of course, the agent could just learn to be reactive. This is what, you could kind of specialize this diagram for supervised learning, for deep reinforcement learning, deep Q learning, for example. But really, if you want the agent to be intelligent, you'd like the agent to be able to reason and plan. And to be able to reason and plan, there's a huge advantage to having at your disposal a world simulator. Okay, so it's this green box here inside of the agent, which takes a percept from the outside world that allows it to kind of get an estimate of the initial state of the world. And then it receives action proposals from an actor. And the actor sends its state to a critic, and the role of the critic is to predict the future expected value of the objective, the real objective. Okay, so it's kind of a predictor for the objective in the long run. So again, getting inspiration from a Dyna architecture, and classical control theory, when the system is meant to produce an action, what it does is that it kind of, think about a sequence of action that could possibly take the world into a particular state, or itself in a particular state that would satisfy its critic. And through gradient descent, it can actually figure out what the best sequence of action would kind of optimize whatever objective it wants to optimize. And then once you have this sequence of action, you can do two things. You can take the action, first of all, and the second thing you can do is you can train the actor to predict the action directly, so that next time you're in the same situation, you don't need to run the simulator anymore. You can just run the actor and just produce the action. So I think this idea actually of producing targets for a neural net by using some optimization algorithm and then training the neural net to directly predict the result of this optimization, I think it's a very powerful concept that I've personally been using in a lot of different situations, but in this particular case I think is really interesting. This kind of idea has been used by people who are kind of at the boundary between machine learning and robotics that use model-based reinforcement learning for controlling robots and things like this. So I'm thinking of people like Peter Abil, Sergey Levin, Igor Modach, Emo Todorov, and other people. Okay, so how do we learn predictive forward models of the world? So one example I'm going to show you is some early experiment that was done a couple of years ago, I mean last year really, although the paper is only 1 year old, by some of my colleagues at Facebook, Adam Lehrer, Sam Gross, and Rob Fergus, where they tried to train a convolutional net to predict the future from a 3D game engine. There is quite a bit of work in this area on sort of learning qualitative physics by Josh Tannenbaum, in particular at MIT, and various people at DeepMind and other places. And so there, it's basically just a conv-net. You give it an image coming out of a kind of a 3D game engine with a physics engine. And you train it to predict where the objects are going to fall in this case, just because of gravity or whatever. And of course, you can just run the simulation, and so you can train the system supervised. Okay, that's a way to do systems identification on this virtual world, if you want. And these are a few results. So what you see here is kind of a starting point on the left of every block, and then the top row is the ground truth, and the bottom row is what the system predicts. And so what you see is sometimes sort of somewhat fuzzy predictions. You see fuzzy predictions here a little bit because it's not entirely clear where this cube is going to fall. Same here. It's a little ambiguous. If you make the towers taller, you get even more fuzziness in the prediction because it's really not possible to tell where the blocks are going to fall. It's an interesting experiment because although it's entirely trained on artificial data, it sort of works on natural data, or on sort of real towers of wooden blocks that are filmed. So that's an attempt of learning qualitative physics in a very simple environment. There is more and more interest in this kind of work now. In fact, both DeepMind, OpenAI, and Facebook AI Research have proposed sort of environments that allow people to kind of play with physics-based simulations to train intelligent agents to do control and do causal inference and all kinds of things. Okay, so let me show you one example of a system that is able to infer the state of the world from text. So this is not from vision, but this is, you have a machine read a text, and the machine needs to keep an updated state estimate of the state of the world so that it can then answer questions. And this system is not trained by reinforcement learning, it's trained supervised to answer questions. So it's being given a text, and then at the end of the text, it's been given a question, and it needs to answer the question, and it's given the answer to the question, and then we train it supervised through backpropagation. It's a recurrent net of some kind to train itself to answer the question. But what it needs to do is that it needs to, because it reads the text before being given the question, it needs to kind of figure out how to store the state of the world and update it every time it sees a sentence that describes an event. So before I talk about this model, I'm going to describe a few work in this area that preceded it, which are basically recurrent neural nets that are augmented by a piece of memory. And in my opinion, this is one of the most interesting developments of machine learning over the last few years, or deep learning over the last few years. I'm actually missing a reference here, which is the dynamic neural computer from DeepMind that just appeared in Nature a few weeks ago. So that started with Oreiter and Schmidhuber's LSTM in the late 90s, where we had the idea of sort of augmenting neural nets with registers, originally to really solve the long-term memory problem and the vanishing gradient problem. And then more recently, there were two pieces of work from Facebook AI Research, one called the Memory Network by Weston, Chopra, and Board, and the second one, the Stack Augmented Recurrent Neural Net by Julin and Mikolov. And both are basically recurrent neural nets where you add a piece of memory to the neural net. Because there is this kind of very curious thing that recurrent nets are very bad at actually remembering things. So if you use a recurrent net and you run it for more than 20 iterations or so, it will have forgotten all information about its initial state, unless you build specific architectures into it, like LSTM or like explicit memories. And in fact, I've learned from neuroscientists that the cortex in the brain is similar. The cortex by itself cannot remember things for more than about 20 seconds. And we know that because there are patients who have lost this separate piece of memory called the hippocampus. So the hippocampus kind of sits in the middle of the brain and sort of innervates a big chunk of the cortex, and it's there as kind of a working memory, episodic memory, etc. And if you don't have a hippocampus, you basically can't remember anything for more than 20 seconds. So nature has figured out that you need a separate entity for storing things, for kind of, as a scratchpad memory or a short-term memory. So what these guys have been doing is sort of various forms of memory. A particular one is in the memory network is basically a differentiable memory. You need a differentiable memory because you want to propagate gradient through it so that a recurrent net that uses it can sort of decide what to write and how to read from it in the process of answering answers. So I'm not going to go into the details of how this is built because I want to talk about the entity RNN. But basically, those systems were used in the past to answer questions, to build a question answering system. So the stack augmented RNN was for a different purpose, but the memory network was, particularly a form of it called end-to-end memory network or weakly supervised memory network, was built for answering questions. So you look at the diagram at the bottom right, a question comes in. So we assume that the memory is stored in the form of a list of vectors, the story that it needs to answer questions about. Okay, so the system reads a story and then stores every clause in the story, every sentence, if you want, in a piece of memory. And that process is kind of handcrafted, if you want. The way the sentence is encoded into a vector is learned, but the fact that each sentence occupies a different memory slot, that's handcrafted. And then what happens is you encode the question in the form of a vector, then you compare this vector with all the vectors in the memory. And with a kind of a softmax type competition, the memory kind of produces an output, which is sort of a weighted sum of the memory entries weighted by those coefficients coming out of the softmax, determined by whether the input vector kind of matches the items in the memory. And then that goes back to the recurrent net that kind of crunches on it and generates another vector for the memory, etc. So that allows the system to learn to access particular relevant facts or sentences in the memory so as to kind of produce an answer. And at the end, you give it the correct answer, you backpropagate the gradients, and you just train it with backprop 2 times, essentially, and you unfold it 3 or 5 times or so. So this system, which came out about 2 years ago, was able to do things like, you can have it read the 15-sentence version of Lord of the Rings, and then ask questions about where every object is. More importantly, Jason Weston and his colleagues at Facebook came up with this list of 20 different tasks that this kind of neural net could be asked to solve, so question answering type tasks. Whether the questions kind of require a single fact or multiple facts or some inference or require counting things, etc. And those memory networks, as well as other models that people have come up with more recently, can solve 18 or 19 of those tasks, but not all 20. In fact, no existing system until now could solve all 20 of those tasks, all 20 types of questions. So here comes the entity RNN. So what the entity RNN is basically sort of a distributed memory RNN, if you want. So it's a bank of recurrent nets augmented by a memory. So each of those module is as kind of a vector state, if you want, which you can think of as containing 2 things, kind of a key for the memory as well as a content for the memory. And whenever a sentence is given to the system, each item, each entity, each memory cell can choose to update itself or not using a gating mechanism, depending on the nature of the information that comes in. So here is a good example. If I say something like, John went to the kitchen, then what the entity network should do is perhaps have a cell that stores the properties of John, and change the location of John to the kitchen. And you should also probably have a memory cell that stores the content of the kitchen and update that with John. And then in fact, I can say, John picks up the milk, and then John gives the milk to Alice, and Alice goes to the living room. So there is a kind of a sequence of events like this, and if too many events occur, then the previous system, the memory network, can't really keep track of too many events. If there's 20 people coming into the room and then 19 leaving, if you count, you know that there's only one person left. But if you don't maintain a state of the world, it's very difficult to do. You'll have to kind of read your memory 39 times to be able to tell. So this system actually trains itself to keep keep a updated state of the world, if you want. And this is the first one that actually can solve all 20 of the baby task. And my computer doesn't want to switch slides. This is a paper on archive so the first author is Michael Henaff, Henaff, and this is submitted to ICLR, so you can also see it on openreview.net. Okay, this machine is really sick, so I'm going to have to completely reboot it, but it's going to take a while. So maybe we can take a few questions before I go to the rest of the talk. Oh, here we go. Came back. All right, so now let me talk about unsupervised learning, really, because that's, if we want to build predictive world model in the real world, we need machines to be able to predict not discrete things, but continuous things in high dimension. And that's really where the complexity of unsupervised learning is. So here is a way to formulate unsupervised learning. There is a very natural way to formulate it in terms of density estimation, but I want to stay away from it for reasons that may or may not be clear at the end of my talk. So let's say our entire universe is composed of two variables, y1 and y2, and what we observe in the world are those points along this curve. So there is obviously a dependency between y1 and y2. If I give you y1, you can probably predict y2 more or less. If I give you y2, there might be two values of y1 that are possible. So there's a dependency between them. And my view of unsupervised learning is that we should have a machine learn a contrast function, which I'm going to call from now on an energy function, in such a way that this energy function, this is not an energy function we minimize by learning. This is not what I mean. It's an energy function that is kind of like a negative log likelihood, if you want, of the data. So it's something that tells you if you are on the near data, real data, or far away from data. It's a contrast function that will take low values on the training samples and higher values everywhere else. And of course, there's lots of different functions that will kind of satisfy this condition. Okay, so training a function of this type, sort of shaping a function of this type by training a learning machine to compute this surface is called energy-based learning. And I've used this for supervised learning in the past, but one of the things you might want to do here is kind of a energy function being trained here. One process to learn this is that you have a neural net or whatever parameterized function you want being fed a y vector, and it produces a single scalar value, which is the height of this curve at this particular point. So if you feed it a point from the data set, you tune the parameter of this function in such a way that the output goes down, right? You want low energies for points that actually come from your data set. And then the big question, the complicated question is, how do you make sure the energy is higher everywhere else? And so a technique, for example, is to pick points randomly or semi-randomly outside of the kind of manifold of data, if you want, and push them up, push their energy up. So tune the parameters of the machine so that the energy goes up. But in fact, there are lots and lots of ways to do this, to kind of make sure the energy outside of the manifold of data is higher than everywhere else. And in fact, you can sort of formulate a lot of classical unsupervised learning algorithms in those terms. You can find the equivalent energy function that those algorithms compute, like PCA, K-means, gas and mixture models, square ICA, etc., and kind of view their learning algorithm in the context of this kind of learning, this contrast function. So for the probabilistic models, of course, it's obvious the contrast function is just a negative log likelihood, negative log density that the model learns. But that's just a special case. So, maximum likelihood works. In that case, you make the probability of the data points high automatically because of normalization. The probability of the other points goes down. But the problem is all the interesting models of probability densities that we want to use are essentially intractable. We can't normalize them easily. And so we have to resort to all kinds of tricks to make sure that, to approximate the fact that whenever we push up on the probability of something, we have to push down on the probability of other things. In terms of energy, that means when you push down on the energy of the data points, we have to push up on everything else around. And so I made a list of 7 different methods to push up the energy of things outside of the manifold of data. One is to build a machine so that the volume of low energy stuff is constant, like PCA, k-means, etc. Push down the energy of data point, push up everywhere else. That's really what maximum likelihood is doing. Push down the energy of data point, push up on chosen locations. So this is what contrastive divergence does, ratio matching, noise contrastive estimation, minimum probability flow. There's all kinds of methods, variational inference. Minimize the gradient and maximize the curvature around data points. That's core matching from Apoy-Varinen. Train a dynamical system so that the dynamic goes to the manifold of data. That's the idea of denosing autoencoder. There is no energy function there. It's more like a vector field. Use a regularizer that limits the volume of space that has low energy. That's the idea behind regularized autoencoders, like sparse autoencoders and things of that type, which were very popular in the mid-2000s among people working on deep learning. And then there is, other techniques. And PCA gives you energy functions like this. So if you train with data set that come from this little spiral here, PCA will give you an energy function of this type, basically low energy on the principal axis and quadratically increasing energy as you move away from it. K-means, K-means gives you something like what you see on the right, where each of the prototypes are put around the surface. It seems to work really well, except it doesn't work in high dimension that well. Sparse coding does a kind of a piecewise approximation of your manifold of data. But all of this, I think, is not so useful anymore because a new idea popped up 2 years ago called adversarial training, or sometimes known as generative adversarial networks. This is a very, very, very cool idea by Yann, who at the time was a student in Yoshua Bengio's lab in Montreal, and since then moved to Google, and since then moved to OpenAI. And I think this is the best idea in machine learning in the last 10 years. Occasionally, I would say the last 20 years. I'm really a big fan of this idea. And the reason why I'm a big fan, I think it's because it's the ticket to solving the main problem of unsupervised learning, which is that the problem of unsupervised learning is predicting under uncertainty. So here is a prediction problem here. Let's say we want to predict the future. So I give you a snippet of video that shows me putting a pen on the table and letting it go. And I ask the system, what is the world going to look like a quarter second from now? So obviously the pen is going to fall, but it's very hard to predict exactly in which direction the pen is going to fall, right? So here this G function here takes the past video frames. It also takes a source of random vectors. That's the Z variable. Think of it as kind of a latent variable. And it predicts the future. And it's going to make a prediction, which is this point Y bar, which is symbolized by the video of the pen falling to the left. But in fact, when we observe the future is telling us that the pen doesn't fall to the left. It falls to the back and slightly to the right. And so should we punish the machine for making the wrong prediction? We shouldn't, because there was really no way the machine could have predicted the correct answer. It predicted something that's kind of conceptually correct, but even if it's not exactly correct. So perhaps what we could say is, the machine, what we want the machine to predict is one point along this red ribbon of plausible futures. And if it predicts a point on that ribbon, we don't want to punish it for it. If it predicts something outside the ribbon, we do want to punish it for it. We want to predict something on the ribbon. Okay, now the thing is, we don't know what this ribbon looks like in advance. And so what we need to do is train another neural net to learn the ribbon. And that's an energy-based model. It's a model that basically learns on the ribbon, produce low energy, outside the ribbon, produce higher energy. Okay? So what I'm going to talk about now is a slightly different formulation of adversarial training than the original one by Yann. So this is kind of energy-based adversarial training, if you want. And really it works like this. You have the discriminator. So the discriminator is really this energy function, this contrast function. Its output is a scalar. It's supposed to be low on the real data point, the blue point, and it's supposed to be higher on every other point. And you train it in 2 phases. You show it a data point from the data set, and you train the parameters of the discriminator to lower its output, okay? Because you want low energies for real data point. And then you pick a green point. I'll tell you how in a minute. And you train the discriminator to now increase its output because the green point doesn't come from the data, it comes from some other process. So now, the list of 7 methods I described was basically how to kind of come up with those green points. But what we're going to do now is train a neural net to generate those green points. So instead of using Markov-Chain Monte Carlo, gradient descent, contrastive divergence, whatever, we're going to use a neural net and we're going to train it to produce those green points. So what this neural net, the generator, is going to do is produce those white points, which are the green points. Every time it produces a green point, the discriminator knows it's fake, so it increases its output. It tunes its parameters so that its output increases. But then the generator is going to cheat because what it wants to do is produce points that are as close as possible to the data. And so it gets the gradient of the output of the discriminator with respect to its input. And with this gradient, it's going to adjust its parameter so that the green point gets closer to the manifold of data. And so eventually what's going to happen is that the green points are going to get closer, and there's going to be an equilibrium when the two things kind of balance each other. The green points are on the data set, and the discriminator can't make the difference. And the generator basically doesn't get any gradient because the energy of those points is already low. So there's been a lot of really amazing success by an increasingly large number of groups on generating images using those adversarial training. Bedroom images, this is the deep convolutional generative adversarial network of Radford, Metz, and Chintala. So Radford now is at OpenAI, Chintala is at Facebook. You can interpolate in the latent space. You can do arithmetics on faces. There's this new form of energy-based adversarial network where we can basically choose whatever architecture we put in our discriminator. In particular, we can put an autoencoder. That's one of the things that we have in our paper. And we have 2 loss functions. And what we can show in this new paper about energy-based GANs is that the optimization performed by the system reaches a Nash equilibrium. And at the Nash equilibrium, the probability distribution of the data produced by the generator, if it's infinitely powerful, are kind of similar to the one of the data. So there's sort of interesting things here. It sort of breaks the usual paradigm that we have in machine learning. We're not minimizing or maximizing a function anymore. We're finding a saddle point using, or really a Nash equilibrium, because it's not a single function. We're kind of minimizing 2 functions. But because one of the functions has kind of the negative of the first, they kind of compete with each other, and there is a Nash equilibrium. Those things work pretty well. So if you use the discriminator as a feature extractor now, so you want to use it to recognize digits, for example, you train it on MNIST, it actually works pretty well. It gets 0.9% error using a fully connected network of a particular type called a ladder network, trained unsupervised using that, and then supervised with just 1,000 samples per category, which is kind of pretty amazing. You can use it to generate images. So this is one of those energy-based GANs trained on the ImageNet dataset, 1.3 million samples, without any information about the category. And so then you just feed it a random vector and you ask it to produce an image, and it produces things like this. So if you are far in the back, there is repeating screen, so I'm not sure, but if you are far from the screen, you may think those are kind of cool-looking images. And if you are in the first row, you realize, what the hell is this? There is no object you can identify in there, right? It's all a mess. It looks kind of statistically correct from far away, but they actually are not any object you can identify. Here is if you train the same model purely on dogs. So you get sort of weird, soft dogs. We are in like Salvador Dali country. I think his house was a few 100 kilometers away from here, so maybe those are Salvador Dali dogs. So another thing you can use adversarial training for is video prediction. You feed that to a convolutional net. And of course, it's just another form of supervised learning in a way, where you feed the system with 4 frames and you ask it to predict the next 2 frames. And if you do this with least square, you get those very blurry predictions that you see at the top right. And that's because what the system predicts is an average of all the possible futures that could possibly happen, and it doesn't know which one happens, so it produces an average, and that's a blurry picture. Here's what you get if you use adversarial training. So again, on the top right, this is L2 least square loss, and the other images are with adversarial training. And so the first 4 frames are observed, and the last 2 frames are predicted. And they're not blurry. Here's another version of this where we predict 5 frames, and those is trained on segments of video shot in apartments in New York, where the camera pans. And so what the system has to do to be able to predict the red frames is to kind of invent what the apartment looks like in places where it hasn't seen it. And it's a little hard to see on this one, but let me look at this. So at the right panel, on the bottom left, there is kind of a bookcase type library. And the system kind of dreams up what this bookcase is supposed to look like as the camera moves. And it kind of makes a decent job at sort of inventing, books and shelves. However, if you let it run for 50 frames, it doesn't quite work. So one thing to understand, so since then, since we produced this work, other people have done video prediction, and they've done video prediction by making assumptions that are relevant to video, like there are objects in video, and there are, it's basically motion of things that don't change, etc. You can do a much better job if you make those hypotheses, but we're not interested in video prediction, we're interested in just prediction. And so we don't want to put anything in it that's specific to video, so we want to use this for text or for, other types of modalities, speech, etc., just a model of the world, physics, etc. Okay, so I'm going to stop here, and thank you for your attention. Basically, I'm going to show the dogs because it's just too funny. But conclusion of this is that what we need to do, what we need to work on, I think, to build intelligent machines is what people would call model-based reinforcement learning. And so one of the things that we are the most interested in at Facebook to work on is model-based reinforcement learning. At some point, we had a reputation of not liking reinforcement learning. That's not true, as you saw. But what we're working on is the whole cake. You need a cherry on the cake, but you need the whole cake. The cherry without the rest of the cake is kind of pointless. So learning predictive models of the world, I think, is the ticket. And then learning actions, and then optimizing intrinsic objective functions is really, I think, the path forward for making progress in AI. Thank you very much.